So welcome to this edition of the Experiences Talk series. For those of you who haven't come to one before, you're sure to be entertained, especially since it's Erik. And my first memory of Erik presenting was when he did this talk of VB, and it was extremely entertaining. And actually, initially, I was a little shocked. From the he's like a complete departure from the normally stayed presentations that you see at Microsoft, and I'm sure from his abstract you sort of expect something dramatic, right? I'm sure he won't let us down. So Erik.
All right. Well, thank you very much. Well, I'm happy to get the opportunity to kind of talk to the SQL folks, and I'm going to reveal to you the one secret weapon that I have. Okay, and I've been milking this secret weapon for many years, and who knows? Maybe the end has come. Maybe today is like this is my swan song. So it's good that you're here. Now, what is this picture here? This picture is a picture of Mondrian. You probably know Mondrian from the kind of, the paintings that have all kind of squares and primary colors. Well, actually, Mondrian started out as a traditional, old-school Dutch painter where he would kind of paint the kind of, the Amsterdam harbor with gray skies and sailboats and so on. And during his life, he became more and more abstract. So his mission was to find the ultimate abstraction where the painting would only convey beauty. And the reason that he used kind of later in his work just primary colors and rectangles was because that is kind of, full abstraction. Okay, those paintings only convey beauty, but there's no depth or you cannot recognize anything real in there. But halfway through his work, like in his middle time, he was you can see that his work is getting more and more abstract. This is called a flowering apple blossom. And so you can still see that it is like that, but it's still abstract. And then when he, at the end of his life, he moved to New York, and I think he started to kind of enjoy the ladies and the booze. And then you can see that, he has this famous painting, Broadway Boogie Woogie. And I think that went downhill from there. It wasn't abstract anymore. But as Savas knows, this is what I'm trying to do in my work. I'm trying to look at a problem and really kind of, get down to the essence and find, what is really the true abstraction that's hiding behind a problem. And then, as I said, there's one secret weapon that I use, and so I'm going to reveal that to you. Okay, and that secret weapon is duality. And you will ask yourself, what is duality? Well, I will explain that. And also I will explain to you in the meantime, what this whole NoSQL thing is about, etc., etc. So the talk is kind of, there's a technical spine, and then I will fill it in with interesting kind of, life lessons of how I do work. But I warn you, don't imitate me, because it will only lead to trouble. People will think that you're weird, and they will kind of go, it's like, oh, Erik again, he has got some package from Amsterdam, So don't listen to me and do the opposite. That is duality in short. Okay, so one of the things is that there's Paul Graham. I don't know if you know, have you heard of Paul Graham? He wrote a really nice book, Hackers and Painters. And one of his blog posts, he is like, well, now he's insulted because he doesn't call them blog posts, he calls them essays, but they're just blog posts. But one of them, he explains, is what his secret weapon is. He kind of, wrote a company that built some shopping website, and then he sold that for many millions. Everybody's dream here in the audience, I guess. But he says that mathematics was his secret weapon, and Lisp. And so I use mathematics as my secret weapon too, and in particular, category theory. Okay, and when people hear category theory and you go to Wikipedia, you scratch your head. It's like, oh my goodness, category theory. That's it. It's sometimes also called abstract nonsense or generalized abstract nonsense. So then you can ask yourself, how can somebody use category theory as their secret weapon? Well, the thing is that category theory is really mathematics done when a computer scientist would invent mathematics. So it really appeals, I think that's why it appeals to computer scientists. And the way they do that is to say, well, if we look at mathematics and we look at groups and linear algebra and whatever, these look all different. But if you then think about what is the interface that is implemented by all these mathematical theories, then you suddenly see that these things are not that different. They're all kind of, concrete instances of a particular interface. Now, when you have interfaces, you then need to glue things together. Well, how do you glue things together? Well, using composition, using function composition. And then you say, oh, what is a function? Well, that's another concrete type. So what is the interface that functions implement? And then you get category theory. So it's really category theory is nothing more than programming against interfaces. And we all know that, right? COM. What was COM? COM is now making a comeback in Windows 8. It's also all about programming against interfaces. Tony Williams should get the Turing Award. If you read the original COM paper, it has deep, deep beauty, and it's very, very similar to category theory because he also distills everything down to composition of interfaces. To what? To COM? As I said, it's back. Right, in Windows 8, COM can never die because it's a fundamentally kind of great thing. We messed up the implementation with the registry and so on, but that doesn't take away that COM itself is like pure beauty. It's gold. Anyway, so category theory is the COM of mathematics. Okay. And I think Don Box, when he wrote about COM, he said, it takes, like 6 months of fog before you understand it, and then you never know why you didn't understand it before. Well, that's the same feeling you have with category theory. All right, and with many technologies it's different. Like Ruby, it's like 6 months, you're on a high, and then you think, what the heck was going on? How can I ever fall in love with this crap? So I like this kind of, the other way around. Anyway, there's another thing why I'm interested in category theory, and that's because I'm Dutch. And there's this phrase in English like going Dutch, where you pay for yourself. That is true. Okay, the Dutch are cheap. We are cheap. For the longest time, I would even buy my clothing at the thrift store because I was cheap. So we don't like to pay money. We don't like to, and also I'm lazy. I don't like to do work. I want to do as little work as possible and get the maximum results. Well, category theory gives you something for that, and that is this thing called duality. And that says that every statement or every theorem in category theory has a dual that you get by reversing all the arrows. Okay? And that's great. And then what it says is that also that every theorem that is true in one category is also true in the dual category. So what that means is you get buy one, get one free. Okay? And that's the thing I love, right? I only have to learn one thing and I get another thing for free. Now you think about this, and as programmers, we're using this duality all the time. If you know De Morgan's law, right? Not A or B is the same as not A and not B. Well, that's easy because now I only have to remember one thing for and or, and then it works just fine in the other case. Well, that's an example of duality. And this is a very, very good thing. And I'm going to show you all the examples of duality that I've used during my career. Okay, and so when I was a young Erik, this is like a long time ago when I still had hair and I was still kind of looked fit. And now, so there was a different guy. You wouldn't remember him. I was wearing tie-dyes. I used to be like a hippie with long hair and so on. So my thesis was about initial algebras. Okay. So what are initial algebras? Well, initial algebras are, maybe you can say it's like classes in C# are an example of initial algebras. It's just data structures. Trees. When you write compilers, you have abstract syntax trees. Those are initial algebras. And so my goal, again, being lazy, was to say, if I like to write compilers, I like to design languages. But writing a compiler is a lot of... who here works on this SQL compiler? Nobody? Good. Oh, there's one. Look at it. Isn't there a lot of kind of, stupid work involved? And so I don't like that. So I thought, well, what if I could take a denotational semantics, a kind of high-level description of the language, crank a button, and then out comes a compiler? That would be cool, because then I could, create a compiler in half the time of everybody else, and then I would go fishing or go to a bar or go gambling. I don't know, enjoy life. So that's what I did. And initial algebras were one thing. And these guys, the Burt-Meertens formalism. This is a Dutch invention. It's called also squiggle, where the idea here was to say, if you look at mathematics and you do physics and you have a differential equation, what do you usually do? And I assume that you still maybe remember a little bit of that from high school or college. When you're solving a differential equation, you have, say, a pendulum, so you write down the model for the pendulum, and then you shut off your brain and you go in automated mode. You're going to solve this differential equation. You have no clue what you're doing. You're just following an algorithm. You're just pushing symbols. And then when you're done, you look at that thing and then you say, now I understand what's going on. Okay, but you start with understanding, then you go to a mechanical calculation, and then you look at the results. Same when you're doing long division. If you have kids, the greatest thing to teach kids is long division, because 100 divided by 5. What is that? Well, you just write this thing down and you go mechanically and out comes the answer, and then you check whether it worked. But while you're doing the long division, you have no clue what you're doing. You're just doing mechanical stuff. So the dream here was to program in the same way. So you would write down a specification of your program in a high-level way, just like a differential equation. Then you would turn down your brain. Being Dutch, you would probably have gone to a coffee shop or something. You go and you mechanically go, and then after a while, the program shows up and it's beautiful, very efficient, etc. So that was the dream of this thing. But as it usually goes, in order to do that, you have to develop other kind of theories, and that was the Burt-Meertens formalism. So what is that about? Well, it started out as a theory of lists. So lists, if you use Lisp or functional languages, that's really the only data structure. For SQL people, the only data structure is B trees. Okay, I've never seen any other data structures in Building 35 than B trees. In the functional programming world, the only data structure is lists. Now, what can you do with lists? Well, here's a list of 4 numbers. And if I write that as a tree, I get this structure. So this is like the empty list. And then I append 3 to it. And then I get a new list. And then I append 2 to it, etc. So now I can do 2 things with the list. One is I can take that list and destroy it. That's what we usually like to do. This is like a query, okay? This is a query, and then this is an aggregate. So an aggregate is like a destruction, and SQL people love destruction, right? It's like every time you do a query, you have a table, and what do you want to do? You want to destroy that table and get a single value out. And that's what this does. And the way you do that, if I want to sum this thing, I'm just replacing each of these constructors here by addition, and magically I can aggregate over the values. Okay? But you see that this is a very systematic process. I'm just replacing each constructor in the list by addition, and that's how I do aggregation. Now, you also might want to say, how can I generate a list? So this is the opposite of aggregation. And so to use this duality thing, this is co-aggregation, okay? This is creation. Imagine that you have a number, and I want to generate a table from that number, okay? Some people want to do that. And for example, the way you do that is usually by having a little state machine that says, you know, it starts at 0, say, and then, or starts at 3, and then every time, you know, it generates the next number until it finds some terminal condition, okay? So just like you can do an aggregate to reduce a collection into a number, I can generate a collection from a number, okay? And this is kind of quite unusual, and this is the one that we most often do. But you see that they are kind of each other's opposites, and they are actually each other's duals. And it's this guy, Richard Byrd, that did a lot of work in this space. And one of the things that he showed is this theorem. So I don't know if you've ever gotten these kind of talks where people show the theorem. I don't know when is the last time that you used a theorem at your work. But this is called the homomorphism theorem, which says that if I have a function that takes a list and aggregates over that list, okay, then I can split that function into two things. One function that is really a projection function. So in SQL, you would call this a projection function that just applies some function to each element in the collection, followed by an aggregation that takes the collection and boils it down. Okay? So every function that's a homomorphism can be written like this. Now, in terms of SQL, you can say every SQL query can be factored into a projection followed by an aggregate. Okay? And probably inside the SQL optimizer, they will do something like this. And now our friends at Google discovered this, and now it's called MapReduce. And now the whole world is like, oh! But it's just a simple theorem from functional programming. I will show you what we can do with this. Okay? But for SQL people, this should be very familiar. Any query can be kind of, you know, factored into something, and then you do the aggregate at the end. Okay, so this was for lists. But now how do we do this with trees or other more complicated data structure? And the nice thing about category theory is that you can generalize from lists to any other data structure and define the same things. Okay? And that's when you get initial algebras. Okay? And initial algebras are finite structures like trees or lists or whatever. And then, if you look at those things, you can take the dual of that, and then you get final co-algebras, and those are infinite data structures. Let's look at the list example for now. Okay, so list is a finite thing, and it's kind of built out of these constructors. So you create a list by calling the constructor. Now, if you go to these final co-algebras, these are infinite objects, and the way you access them is by destruction. So you're kind of, you know, asking us, say you have a stream, an infinite stream. Well, you cannot represent that infinite stream in memory. So the only way you can interact with this infinite data structure is by pulling at it kind of one by one. And then under the covers, it might create itself, but it never, it's kind of, you know, in memory at the same time. So these are kind of the things that follow from category theory. So let's look at these things. So this slide, this is, so I've tattooed this on my back, so this is so beautiful. So here's what you're doing, right? So suppose we have this list, okay, like a list of numbers as I just showed you, and I've shown you how to take that list and create an aggregate that takes that list and turns that into a number. Okay? And I did that in a systematic way by taking all the constructors and replacing them by some function. Okay? So that is this function here. So let's call that, with the banana brackets here. And the way you do that was by recursively reducing or aggregating over the sublists. Okay? Well, that's what we call a catamorphism, and then this thing is called an initial algebra. The other thing that I showed you, when you generate a list, okay, well, we use the kind of opposite things here, and what you do there is you go from a number to a list, but the way you do that is you start with a number, you apply a function that turns that into a number and some other value. If it's the other value, that's when your state machine is done, and then you recursively generate a list from that number, and then you get this list. So it kind of works exactly the other way around. So now you might be confused, say, oh, Erik, you really got the package from Amsterdam today. But I'll make this more concrete and show you where this is useful. But there's one thing that I want to notice here, that these initial algebras and final algebras, one was finite and the other one was infinite. So now if I want to move between them, I have to deal with non-termination. If I have something finite and I must make it infinite, well, I need to add some magic because I'm going from finite to infinite. If I go from infinite to finite, well, things can go wrong because I might have something that doesn't terminate. So there is some magic, like dark matter, that is involved in going between those. And I'll show you later that this dark matter shows up again and again. Yes. Yes. So that's a very good question. This is called a projection retraction pair, where you have two things like S and T, and if you go from here to here, that's okay. But if you start here and you go there, then you lose something. Yes. And so that is probably also the case here. I can go from finite to infinite, because infinite is just a special case of finite. But if I go from infinite to finite, I lose things, because at some point I have to stop. But then I cannot go back because I've lost information. Yep. Anyway, so you can ask yourself, Erik, why did you kind of do all these complicated things and you didn't really properly explain these brackets here? Well, the things, if you look at this guy here, this is one of those homomorphisms. Think of this as a query over a table, okay? And these are the operators in the query. So if you're doing a projection, that's in here, and then you have to kind of, you take the projection and think of these things as select from where, whatever, right? So, and then in that phi here is all the things in your query. Now what you want to do when you build a query optimizer, you want to say, given a query and a composition with some function, I want to, instead of doing two queries, I want to do one query, right? That's, you have a view and a query over the view. You don't want to materialize the view, you want to fuse that query with the view and do it only once. Correct? That's what we're paid for. Well, I'm lazy, so what this thing says that if I have a function composed with a query, I get another query if I can push that function over the operations in the query. So if I can push the function over the select and over the predicate and over the aggregate, then I can compose these two queries into one. And there's a German guy, Thorsten Gerst, that has applied this actually to real kind of query language, to SQL and whatever, and he uses this thing as the basis for his query optimizer. Now the beauty of duality is that says, well, if I know this, I get this for free. Okay? And what this says is that if I have something that generates a collection, I can split that into these two functions. If I can, push the thing from the other side through the operations. Anyway, so the thing is that I didn't have to think all about this because I just flipped everything around. So I got this one for free. But the thing is here is that this is, what the SQL optimizer is doing all the time. You're taking queries and you're trying to fuse them together into a more efficient query. But that was not what I was doing at the time. I said I was doing denotational semantics. So let's look at what denotational semantics does. Denotational semantics, again, sounds very complicated. Who here has done denotational semantics in college? Few people. Whoever has written an interpreter or used an interpreter? Okay, denotational semantics is nothing more than a fancy word for an interpreter. Okay, that's all it is. Don't worry, it's just an interpreter. And now what I want to do is I want to take an interpreter and turn it into a compiler. Because it's usually easier to write an interpreter and then you make it into a compiler. So here's an interpreter for expressions. An expression is either a constant or some binary operator of two expressions. So how do I write an interpreter? Well, I have to replace the constants by themselves, and I have to replace that binary operator, which is my AST, by, say, addition. Okay? Once I do that, now I can automatically generate this interpreter by recursively walking through that expression and computing the value. Okay, so I've separated out the recursive nature of the interpreter and the operations. And another way what people write it is like this. So if I want to evaluate A plus B, I need to evaluate A, evaluate B, and add the result. And if I want to evaluate N, well, that's N. Object-oriented programmers would call this a visitor. Okay? This is nothing more than a visitor where you're giving here the visit functions for each class. So all these things are all the same. That's the beauty of math. We computer scientists always rediscover mathematics, but we call it something different. So if you say that denotational semantics is a visitor, don't say that. Just know it, and then you can use these tricks. Okay? So now, what you want to do is you want to do a continuation semantics. Well, Erik, what is a continuation semantics? Well, if you look at the compiler and you do a debugging, what do you see when you put a breakpoint? You get a stack trace, right? Well, stack is a continuation. So every compiler compiles expressions into something that uses a stack, which is a continuation. So if I want to take my interpreter and turn it into a compiler, I need to introduce stacks somehow. And that is what this does. And now the trick here is you don't have to understand this, but the only thing I had to invent is this function here. And then I can use that theorem before to just compose my original interpreter with that function. And now I get the continuation semantics. And then you repeat that a couple of times, and then you have an interpreter that you can trivially turn into a compiler. Okay? And so I have to do nothing, because it's all just applying these theorems. Now, if you're an old guy like me, people did denotational semantics, but young kids, they all do operational semantics. So I don't know here who had in college operational semantics. So operational semantics is something where you kind of write a machine that executes an expression. So for example, if I want to execute a number, well, that is the number itself. If I want to execute A plus B, well, I can execute A to C, and then I get C plus B. Okay? So that is kind of an abstract description of how, given an expression, how you can execute it. And if I have A plus B, I can take B and execute it, and I get C, and then I get A plus B. And if these turn out to be numbers, I can add them. Okay? So this is a different way of specifying an interpreter that's more operational. And so, and then you can apply this, and you can start with an expression like this, and apply these rules, and then execute it. Or you can use the rules in a different order, and you get the same answer. Okay, and then people say, oh, this is great, because now I can do these things in parallel, blah, 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 blah. Good. So, guess what? Turns out that I can write the operational semantics using the other brackets. So the denotational semantics was something that used the kind of, the banana brackets, and operational semantics are defined using the other brackets. And you can write it like this, but the trick here is that operational semantics and denotational semantics are each other's dual. Okay? And this is something that, when you look at them, they look very different. But then when you kind of try to go down the essence, if you're trying to extract the blossoming flower tree from them, you will discover that they're really related and that they're each other's duals. Now let's look at this thing, which is another application of category tier and of duality. And this is all about link. Okay, so in C# 3.0 we introduced link, and people look at link and say, "Wow, this is like interesting." But really, it's this scary thing from category theory, hidden behind beautiful syntax. So let's look at that. So this guy here, Phil Wattler, like basically all hair. He was the guy that first saw the value of monads applied to computer science. Okay, so it was a long way. The mathematicians invented this way back, and then Wattler in the 80s discovered this, and from there on, and then eventually this came into link. So when you go to Wikipedia and you look for monads, you find things with Greek symbols and all kind of complicated things, and you say, how can this ever relate to link, where I use in C#, and this is like all, how is that possible? Well, that is the trick. That's the secret weapon that I'm using. You understand the Greek, and you turn it into curly braces. Okay, so that is the trick. And it's easy because I didn't have to invent anything new. The mathematicians did all the hard work. Phil Wattler kind of pointed out that it was useful, and then I said, oh great, I can steal that and put it in and work with the people here to put it in the real language. So that's and what is a monad? And this is the explanation for database people. Monads are just collections. Okay, if you look at SQL, what is SQL all about? It's about sets of rows, right? That's what you learn in college. When you do relational algebra, it's sets of rows with all kind of operators, projection, selection, cross product. But then you look at a real SQL implementation, and it's not really about sets. Because if you do an order by, you don't get a set, because you get something that is ordered. So you already have generalized without, so you're really lying. That your professor or whoever wrote a book on databases is lying, because it's not about sets. It's about collections. And also in SQL, if you do, there can be duplicates in a table. That's not a set. And then they say, oh, it's multisets. Well, it's not really multisets. It's multisets with order. Oh, blah, 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 blah. So really, SQL is already something where we have generalized this notion of collections. Okay, everybody agrees with that? So SQL is not about sets, it's about some form of collection, and it can be different collections. Now the other thing is, you can ask yourself, if we're talking about collections, why should we stick with rows as the values in collections? And SQL people have discovered that as well. We have spatial, we have XML. So the things that you stick in your database don't have to be rows. And your database, your tables, don't have to be sets. Now, surprisingly, SQL people have never leveraged that opportunity. So they're still building databases with tables and whatever, instead of saying, hey, maybe we can really use the fact that it's not about tables with rows, but it's really, queries are about this more general thing. There's a collection with values, and I can filter and transform and union and whatever these collections. Well, fortunately, the programming language people are smarter than the database people, and so we did it for you. And that's called link. But now you can steal it from us, and that's why I'm here. Okay, so let's draw some pictures. So what do you need to do with a collection? Okay, what are the operations? And again, I'm now referring back to this idea is I want to find the interface behind any implementation. So if we're looking at collections, what is the interface that every collection implements? What do I need to do with a collection? Well, I need to be able to take a value and turn it into a collection, right? And SQL doesn't really distinguish that. Is if I have a query that doesn't aggregate, does it return one row, or does it return a collection that has one row? Well, you really have to be precise about it, and this thing makes that precise. You go from a singleton to a collection with one value, or you go from a value with collection with one value to a value. If I have collection of collections, I can kind of just union them and take it into another collection, right? That's what you do with collections. If I look here, there's one collection here and one collection of people here. But if I step back, I just see one collection of people. Okay, that's what union does. And then this is projection. I have a collection of things, and now I apply some function, and I get a new collection where the things are transformed. Okay, so I say this is two rows with 5 columns, and I'm dropping the first column, so now I get a new table with all the first columns removed. But you see that there's no reason that these have to be tables and that these things have to be rows. Everything will work. This, if I now write the collections using generics, what you get is exactly monads. The only thing, what monads give you is a way to take a value, inject it into a collection, to take a collection of collections and reduce it to a single collection, and apply a function to each element of a collection. Wow, that was trivial. SQL people do much more complicated things. So the mathematicians are always kind of, they're solving a little problem, and that's why they're mathematicians, and we as engineers solve real problems, but that doesn't mean that we cannot be inspired by the mathematicians and learn from what they did. Okay, so interestingly, not only collections as in SQL are monads, but when you program in C#, you're also using monads. If you're just making a function call or a method call, you're really using a monad that describes the effects. And we should talk about this over beer, but the thing is that every person that writes C# or C++ or whatever code is using monads without knowing it. Everybody that's using SQL and doing queries is using monads without knowing it. And the beauty is that underneath these two things, the same thing happens. And so the world of programming languages and the world of databases is not different. They are the same because under the covers, all they're doing is doing monadic computations. And that's the kind of thing that I'm after. It's like, these things cannot look more different. I've been now here 9 years in the SQL org, and it's like day and night between programming language people and database people. But underneath, the mathematics is the same. And so that's why we can be, we should leverage that because there's a common thing. So for example, you could use the database to execute C# programs. So you can compile C# code into SQL queries. Brian Beckman did this a while back for some, I think, entity framework competition, and he won an Xbox for that. And what he was doing was just using this trick, which is kind of weird, right? So you take IL and you compile it to a SQL query, and when you execute the query, the IL runs. Pretty neat. All right, so now how does this relate to LINQ? Well, everybody, if you know LINQ, you write queries like this, right? That look a little bit like SQL, or maybe more like XQuery. And what the C# compiler does, it turns that into these sequence operators that look like this, okay? And these guys are, again, just monads formulated slightly differently. Now, we have seen that monads underlie SQL, underlie normal computation, and underlie LINQ. Okay, so these are all instances of monads. Now I'm going to use my trick again and flip the arrows. Okay, and I don't know what I'm doing. Usually, you know, Savas will know. I never know what I'm doing. Okay, I'm a random guy. Okay, I'm just doing something. I say, I have something with arrows. I can reverse them. So I had this picture here with these collections. I'm going to reverse the arrows and see what happens, right? That's what mathematics tells me reverse the arrows. So this says, given a collection, I can extract a value from it. Or if I have a collection of values, I can kind of partition it into a collection of collections. And this one remains the same. If I have a collection of values, I can apply a function to each of them. Okay? Well, this is kind of familiar. We all know that group by, right, takes a collection and turns it into a collection of collections. And that one is like, you know, I can extract a value out of a collection. So it's not very unnatural. But I didn't invent this, right? I just reversed the arrows. Turns out that this is comonads. And again, if you go to Wikipedia, they like to use Greek symbols. But turns out that now in C# 5.0, they introduced a way to deal with asynchronous programming, and that's comonads. So not only is every programmer and every SQL programmer using monads, every C# 5.0 programmer is using comonads. So if you look at task of T, okay, has two operations, something called result that takes a task of T, or A, and returns an A. That was exactly that operation, okay? And then this guy here is a different formulation. This is the cobind, so it takes a task of T and then takes a function from task of T to S and returns a task of S. Okay, this is continue with, and if you have continue with, this is homework, you can write a function that goes from task of T to task of T. Okay, that's a simple, and so they're equivalent. If you have a function from task of T to task of T, you can implement continue with. So these are equivalent. It turns out that task of T is a comonad. So C# has comonads, and when I talked to the people that designed task library, they said, "Oh, we didn't know that." But of course they didn't know, because they did the right thing, and the mathematicians had already predicted that. Because that's all what math is. We just have to discover it. Everything is already out there. You just have to discover it. Okay? So task of T is comonad. So now we have monads and comonads, all the complicated, scary things with Greek symbols and whatever. But we're using this every day. If you're a SQL programmer, if you're a C# programmer, all of computation is expressed in these esoteric abstractions. Okay? So now I'm going to show you my latest work, where I say, hey, you know, if I'm going to a conference and all the hip kids, they don't do SQL. They do this thing called NoSQL. Okay? and I feel left out. You know, I like to kind of belong to the hip kids. And then I'm there, and they say, "Are you a DBA?" No. But why are you doing NoSQL? Well, you know, SQL pays my bills. Well, blah, blah, blah. So what I'm trying to do is to say, well, all these people that are out there doing NoSQL, they're doing that for a certain reason. But why shouldn't we, as SQL, also be able to get some of that money from the NoSQL world? And maybe, just like all these other things, SQL and NoSQL is not different, right? Just like, you know, initial algebras, final coalgebras, denotational semantics, operational semantics, monads, co-monads, they were all really the same thing. They were duals. So what if SQL and NoSQL were also not as different as we want them to believe, but they would be duals as well? And now we can do beautiful things. We can make a NoSQL, a SQL Server NoSQL edition, right? And so I've been trying to tell Ted this. I think Ted can double his revenue if we have a SQL NoSQL edition. And I'll show you how to do that mathematically. And Savas over there is implementing that. He can show you that this works, right? This is not something that I dreamt up when I got the package from Amsterdam. This is something that works for real. Okay. I think this is Mr. Ted Cott, the hero of all SQL programmers. He wrote this paper that formalized SQL with a relational model. I think Ted Cott was maybe a good mathematician, but he was definitely not a programmer, okay? Because he didn't understand this idea of looking at things based on the interface and then switching the arrows around. So he's great, but he was really, maybe he drank too much beer. I don't know. Yes, but anyway, that's Cott. So let's look at this thing. So if you look at SQL, the essence of SQL, and again, you know, maybe you guys completely disagree, but I think it is the case. If you look at SQL, every value in SQL, in a SQL model, must have a primary key. Okay? You can have a table that doesn't have primary keys, but that's usually not, you know, not so good, right? So let's say, okay, every row in a table must have a primary key. Agree? Good. So now if I have another table and I want to relate two values, how do I do that? Well, I have a foreign key from the other table to the primary key in this table. Okay? And the usual example, customers and orders. Okay? So there's a customer, and every order has a foreign key to that customer if it belongs to that customer. Now, that is like a little bit weird. Imagine this is parent, and those are the children, right? Now the children know about their parents, but the parents don't know about their children. That's maybe when I'm a sailor, you know, I go to every harbor and I have lots of children. I don't know about them, but the children know about me. That's not a good thing, right? Whereas in programming languages, if you have an object, it has a collection of children, okay? If you model customers and orders in C#, you have a customer that has a list of orders. So there, the pointers go the other way around. Wow. And now you think, well, what is C#? Well, if I have a pointer, really, that is an address in memory, and I can look up that address. So really, C# is a key value store, right? Because each address is the key, and I look up the address and I get the value. So, and C and all these languages. So key value store is just pointers, and SQL, foreign key primary key store, is what we all know, tables of rows. But the arrows were reversed, right? In SQL, they go from children to parents. In the key value store, they go from parents to children. So, NoSQL, which is usually associated with key value stores, and SQL are really deeply related because the arrows go the other way around. So once I discovered that, this I discovered in a dream. I don't know whether this dream was induced by anything, but and maybe there was a package involved, but HR kind of, but it could also be a package from California or Oregon or France, and in a long shape, a glass package. Anyway, once I saw that, I thought, hey, this could be cool, and let's formalize this. So if you formalize this, if you formalize SQL using category theory, and I already was half there, right? Because I just explained to you that collections are just monads. Okay, so I have already kind of had the formalization of SQL ready. If you reverse all the arrows, you get exactly NoSQL, so that's co-SQL. Okay, so I think that's amazing. So NoSQL is nothing to be scared of. NoSQL is just the dual of SQL. So we as SQL Server, we as Building 35, we should go off and build a NoSQL store. Well, that's what I'm doing. But we should really be kind of having an equal team that's building SQL, working on NoSQL. Because I think, as a programmer, I think the NoSQL model is much easier to use. And that's why people in the outside world are using NoSQL. And this is an easy market for us. We have all, everything that we're doing with query optimization and so on exactly applies to NoSQL as well. So I really kind of, go and talk to your boss, and to your boss send email to Ted saying, we need to build this co-SQL store. Okay, we cannot let our customers go and do CouchDB or MongoDB or whatever. They have to use SQL Server, co-SQL edition. Okay, so let's look at, when I talk about the SQL model, it's really any data model that relies on primary keys. And for example, the EDM, the entity data model, is an example of a SQL model. If you go to MSDN and you read about it, it says an entity type, blah, 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 must have a unique key. And then it also talks about sets, because an entity set is a collection of things where each of the keys are unique. And then I have associations, which are foreign key primary key stores. So EDM is just a kind of slightly relaxed SQL model. And ER models are also kind of just SQL models slightly generalized. REST, the web, is a key value store. If you have a URI, that's a key, and now I ask the web, and I give it the key, and it returns to me a resource, or a representation of a resource, which is the value. So the web itself is an implementation of a key value store. So every day everybody is using a key value store. And it's called the web. And it's quite efficient. I mean, I think I can search quicker the whole web using Bing or Google than I can search my inbox using Ease or something, all right? So the key value stores can be really efficient. All right, so this is just a picture to show you how these things are reversed. I've already told this. So, and this is a picture that puts SQL and NoSQL side by side. So this is a SQL model. I have entities that have keys, and I have relationships that go from foreign key to primary key. And then here I go a key, and I can look up, I get the value. That value can have other keys. So the children, the parents point to their children. I would argue that as programmers, key value stores are much more natural than foreign key primary key stores. Okay? If I write a C# program, none of my classes has a primary key. Okay? I don't know about you guys, or you write C++ or whatever. No type has a primary key. Right? That's a very unnatural thing. It has an address in memory, it has an identity, but it doesn't have a primary key. And if you look at memory, computer memory, it's a key value store. So all our computers have a key value store built in, and a very efficient key value store. You give it an address, you know, in binary, that's the key, a 32-bit number or 64-bit number. You give it to the memory, which is the key value store, and it gives you back a value. Okay, so key value stores are everywhere. So we should build a key value store as well, GoSQL edition, where we can give people, where we can make some money on this NoSQL stuff. Okay, and this is C. So the other thing is that neither is more natural, right? In certain cases, SQL data model is really, really good. In other cases, the NoSQL model is really, really good. And we should not pick between them, and we don't have to, because they are mathematically deeply related. So there's no reason to kind of, pick one or the other. And I think we're just plain stupid if we just stick with one. We also have to kind of, use the other. Can you mix them? Very good question. And yes, it's even better. If you look at mathematics and you look at the definition of duality, it says when you have two things that are dual, you reverse the arrows, but the objects are the same. So, for example, I can implement a key value store in SQL by just having a table where the keys are the primary key and the values are the values. And if I do a lookup, I just do a simple kind of primary key lookup. So I can build a key value store on top of SQL. And that's what we're proposing. Or I can implement a foreign key primary key store in terms of a NoSQL store. That's what SQL is. Because in the end, the machine that we have is a key value store. A file is a key value store, right? I give you an address and it gives you the value. So SQL itself is implemented on top of NoSQL, on top of the lower layer. So these things are isomorphic. So you can move between them. And so you can, of course, you can mix them. I can, in my SQL store, I can store a document or a web page or whatever that is, so they're completely compatible. Exactly. Yep. Ah. Yes. So I'm not sure that you can do it fully automatically, but if you look at what Link to SQL, for example, does, I don't know if people are familiar with Link to SQL or Entity Framework, what you do there, or every OR mapper, they do exactly that. You take a query expressed over a key value store, because it's like an object model with pointers, and you compile it into a query expressed over a foreign key primary key store. And as I would argue, you can also go the other way around. So it's kind of obvious, and like none of our competitors, all the people that built MongoDB and CouchDB, they don't know this stuff. We know this stuff. We have done this. So we should kind of really leverage that. All right. So another thing, one thing that I want to, given the time, I will just touch on that. There's a lot of consequences that are kind of, follow from this duality. So there's a lot of things that you are forced upon you when you pick a foreign key primary key store or when you pick a key value store. For example, one of the reasons that people in the real world use NoSQL is because they don't want to schematize their data. Whereas in SQL, the SQL engine relies on the fact that data is typed. Why? Because at least it must know where the primary keys are and where the foreign keys are. Otherwise, you cannot do a query. But if you're building this giant distributed system that has to be up 24/7, you cannot stop it to make a schema change, right? You cannot say, oh, let's stop Amazon.com because we have to do a schema change and we have to kind of reload all our tables. That doesn't work. So people, to get this flexibility and this high availability, they don't want schemas. And maybe they don't even know the schema because I'm storing documents and the schema changes. So schemas, these people are using NoSQL because in SQL you're forced to use a schema. Whereas if you look at the key value store, well, the values are completely opaque. Your memory just stores bits. It doesn't interpret. It's the application that interprets that. It's not the store that interprets that. So again, it's like a duality there as well. So either the store is typed or the application is typed. So you can make this trade-off. Okay. Let's, yep. Exactly. So these are the things that you're making an excellent point. When you're building a system, you're making trade-offs like that. But one problem with using foreign key primary keys is that now I've taken this value and I've normalized it over two different tables. And now I better make sure that these two tables live close together because I need to maintain consistency. I have to do cascade delete, which then it goes against scalability. Because if you want to shard your tables, you have to make sure that everything that's reachable goes into kind of the same shard. So, and so again, it's like, what I'm trying to say is that there's no one true data model. When you're building an application, you kind of pick and choose. In the small, you might say I'm using a relational table because it's very efficient. I can normalize it and don't have duplication. And then in the large, I'm doing a key value store because I need to get other constraints. So, and I think we in Building 35 make the mistake that we're trying to jam everything into SQL and into a foreign key primary key store. Whereas if we would be just a little bit more open and say, look, they're just stores. We're the platform for all data. Relational data and non-relational data, but let's not put the non-relational data in a relational database per se, because, well, we are even implementing a relational database on top of a non-relational database. This is my last example to show you that there's even more interpretations of these monads. So when I talked to you about collections, I said, oh, these are kind of these like woolly things where you can combine them and whatever. But you can also look at different ways of dealing with collections. For example, in SQL, when you're doing a query, if you look at the QP, it's pool-based, right? You get this iterator. And if you want to get the next value, it will go and compute the next value. And so you're pulling, it's like you're pulling the data out of the database, right? And if you look at the implementation, it uses actually a pool model underneath. Now, if I look at my mouse is a database as well. If I move my mouse moves come out of this database. And there's a lot of data in this database. It's amazing, right? Look at how small this thing is. And it has more data than in SQL Azure will ever have. If I move it long enough, right, it will produce a lot of data. It's infinite. Whereas SQL Azure will always be finite. And what is this? This is push. The data gets pushed out of here. But both are collections. And both can be queried using monads or using LINQ or using queries. And so the same techniques can be used to optimize SQL queries as queries over mouse moves. Okay, and if you look at the pool model, that's enumerable. And if I massage that a little bit, because I want to get arrows that I can reverse, you see that the enumerable, get enumerator. And what is an enumerator? Well, that has move next, which can either give me a value, or it can throw an exception, or it can say, I'm done. Okay? So now if I combine the enumerator and the enumerable, I get this thing. This is get enumerator, and this is move next. Okay? Whenever I call move next, I get a value. Okay? I'm going to reverse the arrows. Again, you see that I'm really lazy, right? I'm doing the same trick. I've shown you now my secret. I have one trick, and that's reversing arrows. And that's all I do. It's amazing that Microsoft still pays me money, because I know only one thing is to reverse arrows. It's embarrassing, really. And you invited me to talk about, it's like one simple trick, reversing the arrows. Look at this. That's all I do for a living. But turns out that if I now look at this thing and kind of expand it, I get subject-observer or stream-based queries. So these are also duals. Okay? So now I can write queries, and this is the interface. So now I can write queries like where and select and whatever over streams of data. And they are exactly the same. I can take a mouse move and say, filter out all the mouse moves that are, within this quadrant, and then transform those mouse moves into images or something. So I can write queries over mouse moves. And that sounds, that sounds really kind of wacky. But when you think a little bit more about it, it's no different, because mouse moves are just another collection, just like a table. Okay, so we should also sell the SQL Server Streaming Edition. Well, we have Stream Insight. That's a good start. Stream Insight is the SQL Streaming Edition foreign key, primary key part. Then what is the NoSQL part of that? That's called the reactive framework. So there we have SQL and NoSQL as well for streaming, just like we have SQL and NoSQL for pool. So everything just falls apart. So we have many of these things, and we should make money on every one of them, not just pick one. All right, I'll skip this based on the time. And I want to show you one last thing to pull the circle. So I mentioned in the beginning that this theorem from Bird, the homomorphism lemma, was used to do map reduce. Okay? And so if you look at map reduce, you see here, I do a map followed by a reduce. And so really, this is nothing more than applying this theorem to distributed queries. Now, in SQL, in the optimizer, we've done a lot of other transformations. Now the question is, can we use these other transformations, just like this simple one, to apply them in the NoSQL world as well? So usually, these guys are NoSQL, right? Because it's like really a key value store here, and you get the key value store here. So MapReduce is usually done over NoSQL store. Can we steal from SQL, from the SQL optimizer, other tricks that we can apply to NoSQL stores, and can we use them to do distributed queries? Okay? So one of the things that SQL Query Optimizer does, it takes something that has a lot of joins, and it will flatten the query to do, I think what they call it, a left deep join. Am I kind of smoking crack here? So that's, you kind of normalize your query to flatten it out. You don't want to have nested joins. You want to have like a sequence of joins, and then, you can do other kind of things. Well, that is a trick that I'm going to apply. So I'm going to say, can I take arbitrary link queries, think of SQL queries, and compile them into MapReduce form? And one of the things I have to do is I have to remove nesting. Okay? So I have to take a query that's nested, and I have to kind of, turn that into this linear sequence, this deep left nested join or whatever, and then I can run these things kind of, after one after the other. So this is Strachey, interesting character. He's the guy that invented denotational semantics. He was in Oxford, mathematician, very, very interesting guy. So if you look at what I'm trying to do, is I'm trying to take a query that looks like this, that is nested, which is really, not very nice. And I want to turn that into this query, which is unnested, where I'm just kind of doing this query kind of, one after the other. And as I say, if I look at the database literature, this is called a left deep join. But the interesting thing is that there's no nesting going on. Here you see this is like all deeply nested, and here they are not nested. And this one I can run as a pipeline. I can just run this query, pipe the results in the other one, pipe the results in the other one. Whereas here I have to kind of, like this is like a nested loop that I have to. So how do I do that? Well, turns out that this is a continuation semantics that goes way back to what I did in my thesis when I was trying to get from an interpreter to a compiler, and I was trying to do this continuation semantics, but to introduce stacks. Why do you introduce stacks? Because you want to do things in a certain order. Well, if you want to compile your queries into this non-nested form, it's like introducing a stack. You want to do them one by one instead of nested. And here you see that I'm using transformations like this to unnest my query. Now, if you ask, if you go and look in the SQL optimizer, you probably will see select many, that's cross-apply. You will see that the SQL optimizer will have many of the same rules in there that will take your SQL query and normalize it into a more optimal form. What if we would say, hey, let's take this query optimizer and apply it to this NoSQL space? Now we can kind of blow CouchDB and MongoDB out of the water because we have like decades of experience with this stuff. Okay? And the only thing we have to do is we have to generalize from sets of rows to just general monads. And all these laws look familiar. This is just, this one shows if I have a cross-apply with a nested cross-apply in there, I can write that by a cross-apply, followed by a cross-apply, if that variable, the correlated variable, doesn't appear in the inner query. Very good question. Good. You paid attention. You kind of you have an A. It's other good question. So if you look at the query optimizer, I think it's doing two things. It's doing structural things like this, and then it's doing cost-based or other optimizations. Now the thing is that that works for SQL because I know this table has a certain size and so on. But for my mouse, what is the size of the data in this mouse? I cannot make any estimate. Well, maybe if I know how long the battery will last, but for the mouse, the optimization would be the dual. There I want to see if I have an event stream. If I'm doing a join between two event streams, I want to know which one has the events that are more dense than the other. So there's a duality there too. It's like between space and time. So you're using the same statistics, but in a different dimension. So when I join two event streams, I want to kind of take the one that has the least events and then combine that one has the most events. Just like when you do a join, you want to take the smallest table on the left and the largest table on the right or whatever, right? So you get the same things, but slightly more generalized. So the statistics are there, but if you're in a different domain, you use different statistics. Okay, well, I don't want you to understand this, but if you look at this thing, it is just applying the same techniques that I used in my thesis, but then to turn these queries into flattened queries. And then in the end, you get this thing where I can take an arbitrary query, and here you see where you get this kind of, unnesting. If there's a nested query here, it all kind of, disappears there. Oops. So this is my last slide. So I've shown you my secret, which is category theory, and not even all of category theory. I'm too stupid for that. The only thing I do take from category theory is reversing the arrows. And I hope you've seen all these applications of reversing the arrows: monads, co-monads, streaming, non-streaming, SQL, NoSQL, and that we can use the same techniques to optimize queries. And it doesn't matter because these queries are expressed in terms of monads. So it doesn't matter whether they are streaming, whether they're pool-based, whether they're over SQL or NoSQL. If you kind of express your optimizer in terms of those monads, you can kind of reuse them across all these domains. And then when you target the specific domains, then you're using domain-specific optimizations like statistics about the table size when you have a pool-based thing, or statistics about the density of events when you have a push-based thing, or when you have a distributed one, you're using things like how close is this machine to that machine, and then you're trying to kind of minimize data movement. But those are things that are kind of separate from the general query optimization that you do, to remove nesting and so on. All right, so I hope that this inspired you a little bit. Math is not scary. It's a secret weapon. There's plenty of other math to steal. And I do believe that there's a lot of money that we're not getting at by only focusing on this very subset of this whole rich domain in this building. We're only looking at tables of rows, whereas the world is much richer. There's push, pull, NoSQL, co-SQL, and we should do everything. So we can, I would say we can at least increase our revenue fourfold if we would stop doing only SQL. And so that is, I hope that that's the outcome of this, that somehow somebody that has influence, not like me where I'm just a clown, but where somebody can say, okay, let's really go beyond SQL. Let's make this thing a platform for all data, but really a platform for all data, instead of sticking it in the regular database. And we have all the theory here, and it's just generalizing what we already do. We have decades of experience. We are in the best position to do this. None of our competitors knows this or can do this. And you see it when you look at the NoSQL stores. They started out simple, and now they're adding all kind of optimization. So they're coming from the other side. And if we wait too long, they're smart kids too. And they will then, and then we will be, I don't know. Then it's time to sell my stock. But I don't think it has to go that far. But we should kind of, march up to the people that have decision power and say, let's do this. And we can do this. So that's my story. Thank you very much. And if you have any questions or you want to play with the NoSQL store, ask Savas. He can do demo. And it's beautiful. It makes me cry every time I think about it. Thank you.